Welcome back. In the previous lecture, we talked about the foliated and non-foliated rocks, and this is one of the best example of non-foliated rock, that is marble. And we are fortunate to have such a beautiful monument in India, which is completely made up of marble. And this is one of the reason because the marble is quite hard as compared to the other other foliated rocks. Okay, so let us move ahead. This is again a very beautiful internal structure of from Agra. Probably not from Agra. This is from I think Red Fort. Okay, so this is the picture of that, again made up of marble, and the upper story here we are having, that is also made up of marble of Qutub Minar. And then we are having other examples which used the Makrana marbles from India. Okay, the temple in Birla Mandir in Jaipur, and then we are having the famous mosque in Abu Dhabi, and then we are having Victorian Memorial in Kolkata. So these are all monuments which were been made using the marble from Makrana marbles. Okay, so again very quickly, if we look at the increase in temperature and pressure, how it affects the formation of different type of rocks. So for example, the process here has been termed as you are having diagenesis, you are having low grade metamorphism, and you are having high grade metamorphism. So when you have for example the shale, which is in sedimentary rock. So if you are having the shale here, which is a sedimentary rock, and when it is subjected to the low grade metamorphism, it will result into the formation of slate. Further, if you move towards the high grade metamorphism, or within high grade and low grade, you will have phyllites, and further maximum in high grade you will have cysts and gneisses. Okay, so this is what we were talking about, the for wavy texture, and this we are having the cystose texture. So cystosity will be seen where you are having the slightly larger grains, and you are having the foliations of the platy minerals here. Okay, so you have the composition. If you take, you will have clay, then you are getting into chlorite, muscovite, and then biotite, mica, garnet, kyanite, and sillimanite. And then in most of these rocks you will have the quartz and feldspar, which has been seen. Okay, and then if you move from your left towards the right, you are getting into the high increase in metamorphism, that is increase in temperature and pressure. Okay, getting from low grade to high grade metamorphism. And of course, this is the last point. If you go deeper into the earth, you are reaching into where the melting of rocks will start. Okay, so please remember this, and you can refer the second slide or the third slide where we are talking about the different type of rocks when they are subjected to, like shale to slate, and then phyllites, and then cyst and all that. Okay, so of course this depends on then what you are putting in. Okay, so you have a sandstone which is rich in quartz and feldspar, you will have out product will be quartzites, and if you are having limestones, then we are having the out product is marble here. Okay, so those are the different type of what we talked about, non-foliated and foliated rocks. Now with that understanding, let us look at what is the importance of those rocks. Okay, how they are, we can say that this is the massive hard rocks, or they are soft rocks, and whether they will be subjected to the very fast erosion or not. We'll see that. Okay, for example, slates, and as we have talked about that the slates are the out product of your shale. Okay, and shale is the argillaceous sedimentary rock, so they are having the clay minerals, abundant clay minerals in that. Okay, so they are definitely argillaceous fine grained rocks, shale, and when they are subjected to metamorphism, they will result into the formation of slates, and slates are foliated rocks. Okay, so they are fine grained, impermeable, cleavable, and soft in nature. Okay, incompetent, cannot withstand great load. Okay, so if you are having coming across slates, you should avoid putting any heavy structure on that. Okay, but since they are impermeable and split easily, thin large size slabs of uniform thickness. Okay, this is because of its typical platy nature or the cleavable planes you are having. So you can excavate or extract the thin large size slabs, okay, and which people have used for roofing purposes. So in many places or the many states, they use this as to put the roof as roofing purposes. Okay, economic importance, since they are bad conductor of electricity, used in electrical industries for switchgear boards and all that. Okay. Now coming to gneiss. Gneiss rocks are rich in silica, and that is predominantly quartz and feldspar along with garnet, pyroxene and hornblende. Non-porous and impermeable nature increases the strength of the rock. So this is comparatively having better strength than this one. Okay. Foliated characteristics to some extent improve the workability. Okay. So they are also easily workable. Okay. So as compared to what we see the gneiss is. Load perpendicular to the foliation. Okay. Foliated planes give more strength, so or stronger foundation. Okay. So this is one advantage of this one. Okay. So load perpendicular to the foliations gives more stronger foundation, but if they are inclined, or if the load is inclined, then you will have problems. Okay. So if the foliations are like this and you are putting a lot of load here, then they will result into the slipping of that. So it may result into the slippery. But if you are having perpendicular and then you are having the load here, there is no problem in that sense. Okay. So if the mineral assemblages is more or less similar to granite with less mafic minerals, okay. So they are having more felsic minerals here. The granites, mostly the igneous rocks, are having. So, and if you are having gneiss, which is granitic gneiss, it is also used as building stone. Okay. Also aggregate for making concretes, as road construction, etc. Okay. And then you are having cyst. So this we were talking about the granitic gneiss. Okay. So if the composition of the gneiss is very much similar to granite, then they can be used as a building stone for making concrete aggregates and all that. Okay. Now coming to the cyst, mainly composed of prismatic or platy minerals. Okay. Cyst. Okay, which contributes to development of the cystose structure. Example, the minerals are hornblende, tourmaline, selemonite. Okay, and then you are having chlorite, muscovite, biotite, talkyanite and all that. So these are platy minerals. Okay. So cleavable nature of cyst is the main reason for their weakness. Okay. So they are easily cleavable and hence they are incompetent in nature as compared to the gneissican slate. Okay. Then coming to the quartzite, as we were talking about, that the interlocking of the grains is very much and they are what we call very high, and what we call the granulose texture type we will see. So sandstone composed of quartz and feldspar mineral when undergo metamorphism will result into the formation of quartzites. Okay. So granulose textures, we have structures which we also term as granuloblastic textures or texture, makes them more competent rocks amongst all other metamorphic rocks. Okay. So they are massive, very hard. Okay. So metamorphic rocks, metamorphism sandstone results disappearance of the cementing material, bedding planes and fossils content, if any, in that. Okay. And then result into the formation of quartzites we are having, which is very much most competent rocks amongst the metamorphic rocks. So quartzites are compact, hard and strong than the parent sandstone also, because you don't see any pore space, everything has been squeezed out. Okay. So predominance of quartz makes the rocks very hard, suitable for road construction and concrete aggregates. Now if you look at nowadays, that most of the quarry you are having is they are trying to quarry the gravels, okay, from the older river beds, and in Punjab and all that, most of they are using the quartzitic pebbles. Okay, so they are breaking into the aggregates and using that aggregates for the construction of roads and all that. So the roads which have been constructed using this aggregates, that is mainly of quartzites. Okay, quartzite from quartzitic pebbles or quartzitic gravels will have more durability as compared to when they are been made. The roads are made using the aggregates which are from basaltic rocks or the igneous rocks. Okay. So they act as in good foundations for the sea structures. So this is one of the best example of quartzite which we see. Okay. So I stop here. So we have talked about the different type of rocks, and from my next lecture I'll start and talk about the seismic interior and related to earthquakes, and then we will talk about the seismic different type of seismic waves and their related hazards and all. So now this is another part of this course which is extremely important, and here we will talk about the interior of Earth. Partly we discussed when we were talking about the plate tectonics. Now we will talk about the seismic waves. We'll talk about the earthquakes and how different seismic waves are affecting when they are produced during an earthquake. Okay, so interior of Earth we understand and we know that the interior of Earth is not homogeneous. It is having different layers and of different density and different composition. Now, how seismic waves played an important role to identify and to know the interior of Earth. That is, the interior of Earth is not homogeneous, but it is having different composition and different density. So this we discussed on that day during the initial lecture on plate tectonics, that we have the different material. Even we have different like oceanic crust and the continental crust, and oceanic crust are heavier as compared to the continental crust. Oceanic crust are mainly comprised of silica and magnesium rocks, whereas the continental crust we have silica aluminum and silica magnesium rocks, silica and magnesium rich rocks. Okay, so they are comparatively lighter, whereas the oceanic rocks are comparatively heavier. And then we are having different discontinuities between the major and minor layers within the interior. So if we divide the interior of Earth in the main sections, so what we are having core, mantle and crust mainly, and then we are having further class categorizations, or we are having inner cores, and then we are having outer core, and then we are having mantle, where the mantle comprise of lower mantle, then middle mantle or mesosphere, then we are having a stenosphere, and then we are having the lithosphere part, and the top part what we see is the crust. Okay, the thin part over here. So we have different layers, and this were been identified using or with the help of the seismic waves. Okay, so let us move ahead and then see what so this I'll just move faster. We have already discussed, but I would again request you to go through this, which will help you in understanding the interior of Earth. So as we go deeper into the interior of Earth, we understand the temperature increases along with the as we move towards the interior of Earth, and pressure also increases. Okay, and these are the two graphs which shows the curves which shows the increase in temperature rise of the continental lithosphere, and here we are having the rise and the of the temperature when we look at the continental or oceanic crust mainly, and this red one is your continental lithosphere. So seismic wave, basically we will see what different type of seismic waves are. Okay, now if we would have the interior of Earth as homogeneous, then any earthquake which would have triggered at any location, and the seismic would have traveled like this. Okay, but we don't see this. Okay, we don't see that very systematic travel path of the seismic waves in the interior of Earth. Okay, So if you look at the different type of waves, we have the body waves, which we call primary and secondary waves, P wave and S waves. And if you look at the equations, we are having the P wave and S wave, the velocity equations. So most important here is what we see, the shear wave, modulus of shear wave, or then this one is the bulk modulus we are having, and this is the modulus of rigidity. Okay, and this plays an important role in terms of the S wave. We will discuss about this one. Okay, so we have the density here. So the velocity will be affected by the density, will be affected by the rigidity of the material. Okay. So here, if you look at the interior of Earth, we are having the P waves and the S wave, which are traveling into the interior of Earth, but the velocity changes as you move further into the interior of Earth. Okay, so the slowly it increases here. Okay, but at some places it is like dying out, and then you are having it doesn't travel further. Okay, whereas here in terms of the P waves, it increases and increases. It goes right up to the 11 to 12 kilometer per second, and then it reaches further high. Okay, that is in this zone. Okay, and then you are having further, it reduces, and then so the velocity reduces because of the change in the density or the composition between the mantle and the core boundary here, and then further it slowly increases and so on, and passes through the interior of Earth, that is the inner core side. Okay, and we know that this is liquid. Okay, compared to what we are having completely solid inner core. So if you look at the upper part, there's around 1000 kilometers of the cross section. What you see here is you are having the change in the velocity here. Okay, at this part, so you're having this zone is what we term as the low velocity zone, and this is representing your asthenosphere. So both the seismic waves, okay, which has a speed or the velocity in the crust, so around that, this is an S wave having 3 kilometer per second, and this one is around 6 kilometer per second. It reduces here, okay, sharply, and then further it gains. Okay, but and then it travels again, it regains and travels into the interior of Earth. But this is lost here, it doesn't transmit it further into the interior of Earth, but this has a capability again, and this all depends on the nature how it propagates. Okay, so these are having the S wave and P waves are having very different nature of propagation. Okay, so that we will try to learn here. Okay, so what is the nature of propagation. So further ahead, seismic waves, we have body waves, and we have where we have P waves and S waves, and then surface waves, we have Love and Rayleigh waves. Okay, so P waves, basically the motion, okay, or the direction of propagation, if you look at, is always almost in the compressional fashion. So if you push and pull any material, okay, it is very much similar to that. Okay, so if you hold the spring here and try to push and pull, okay, so if you're having that, so it will travel the particle in this direction. So the movement is in the direction of propagation, but it will pull and push and pull the particles. Okay, so this you will have a very typical nature here. So they are basically the compressional waves, or we term that as in primary waves. Motion is in the same direction as the direction of propagation. Okay, fastest wave, which arrive first, and then we are having the speed is almost like 6 kilometers or 6.5 kilometers per second. Okay, it pushes and pulls the ground. Okay, produces sound. So the movement, it's like what the motion is very much similar to the sound wave. Hence, it will result into the it creates sounds when it is propagated into the atmosphere, okay, or within the Earth's surface. But you can hear the sound when these waves are propagating, okay. Can propagate through solid, liquid and gas media, okay. So it can propagate through any medium. It is not having the restrictions of propagating through any particular medium because of its nature, okay. So it's produced, these are the typical very important points which you should remember. So these are the fastest waves. They propagate in the direction of propagation, or the motion is almost like in the same direction of the propagation. They pushes and pulls the ground, and they can propagate through any medium like solid, liquid and gas, okay. Then another one is what we call the S wave, or we also term that as in transfer waves. So if you hold the rope and fix on the other side and wave up, okay, so it will travel in a very typical fashion, moving the rope up and down and then propagate in the direction of propagation, okay. So if this is the typical of what we see, the secondary waves, okay. So it will move the land surface up and down when it is moving, okay. So it is also termed as the shear waves, or the transfer waves, or secondary waves, okay. Motion is perpendicular to the direction of wave propagation, and the P waves were having almost in the direction of propagation. This is having the perpendicular direction and then arrives later because they are slow speed is slow, almost half, 3 to 3.5 kilometer per second, and moves the ground up and down, okay, and can propagate only through solid. So this here is the most important part where we were talking about the shearing part, okay. So shearing will not take place in liquid, hence it will not allow these waves to propagate further, okay. So there is a damping effect, the energy will be completely lost, it will not propagate further because of its nature of propagation, okay. So it shear, and the shearing is not taking place, whereas in the case of the P waves, we are having push and pull, so it moves in the direction of propagation, and it can go through with a lesser speed also, it can go through the different type of material or the medium, but here this doesn't move in other medium other than only it can go through solid, okay. So this is another typical characteristic of the secondary waves, or we can say shear waves or transfer waves, okay. So motion is perpendicular to the direction of wave propagation, having comparatively lesser speed, almost like half, having in the crust, and then moves up and ground up and down, can only propagate through solid. So this you should remember about the difference between the P and the S waves, okay. Now if you look at the interior of Earth, and if you, for example, say that the earthquake was triggered at 0 degree, okay, then what you will see is that propagation, as we have discussed, that not all waves will go through the interior of Earth, okay. Some are reflected, some are diffracted back, okay. So if you look at the this black lines, all are having, you are having the these are S waves and these are the P waves we are having, okay. So what we see, because the velocity of the P waves changes at the different contact, and the contact between the mantle and the outer core which is liquid in form, and so the S waves will not go through, whereas the P waves which are coming here slows down, and that what we call, it will be slightly deflected, and then we are having further refracted ones which are reaching at in this location, okay. So only what we see, the arrival or the recording of the P waves in this area, we see is because of the what we are getting, the refracted P waves, okay. But no S wave we will be able to see in this region, okay. So no S waves are been seen here, only the P waves are been seen in this area, okay. So what we term this region So we are having like shadow zones. Okay, we say this as an shadow zones. So and this shadow zone from 103 to 180 is complete shadow zone of the S wave. Okay, so no S wave will be seen between like 103 up to 180. Okay, but between 180 and 143 you will be able to catch P waves, okay, which are refracted P waves. But again between 143 and 103, because of the deflection of the P waves, you will again not be able to see the P waves in this region. So the important is that we are having the shadow zones of the S wave. You are having from 103 degrees to 180, and you are having the shadow zone of the this is S wave, and then you are having P waves. You are having from 143 degrees to 103 degrees. Okay, so this you should remember about the shadow zones of different waves. Okay, so this is all like very well seen or observed when an earthquake is triggered at one location, and some stations will be able to record the partial P waves, whereas some locations or some stations will absolutely not been able to record the S waves in that region. Okay, so this is the example which we were talking about. So here we will not see any direct P waves, hence we term this as an P wave shadow zone, and then so that is 103 to 143 is the P wave shadow zone, and from 103 to 180 degrees we are having S wave shadow zone, because S wave will not go through the core, they are been deflected from the outer, that is the contact between the mantle and the core. So they will be seen only in this region, they will not be seen in this area. Okay, so we are not having any S wave which is coming into this area, whereas some P waves will be seen, which will be will be getting within this one, but leaving this part as a shadow zone. This we are having between 103 to 143 is the shadow zone for the P waves. Okay, and the S wave remains completely from 103 right up to 180. Now, for example, you trigger an earthquake over here. Okay, and then what will happen? Okay, so we are having the pink one is your S wave, and blue ones are your P waves. Okay, so the stations which are located here, this one here, okay, this one and this one, okay, will have they will record both P and S wave. Okay, and here what we see are some of the P waves are refracted, and you are having the P waves which are been reaching here. So stations which are sitting just opposite to this, what we have been talking between 143 and 180 will all receive your P waves. Okay, but no P waves here, no S wave here, right from this to this one. But these stations will be fortunate enough to receive all the waves. Okay, that is the P and S wave. So this is what we find and we observe when a big earthquake or even the smaller earthquake occurs on the earth. Okay. Now S waves, as we have been talking about, that they will move the surface up and down. Okay, so they will damage the civil structures which are sitting on the surface. Okay, so it will move surface up and down in the direction of propagation, and this is one of the example of 1999 Chichi earthquake of Taiwan, where you can see the passage of S wave across the area. Okay, so which resulted into so an up and down here you see because of the S wave, and this is the photograph of 2001 Bhuj earthquake in Kutch, which resulted into the preservation of the S wave. So waved up surface, if you take here, this is a bridge which shows very beautiful preservation of the passage of the S wave here. Okay. This is on the bridge and this is on the ground we are having. So if you carefully watch this, there is an up here, down here, up here. So this is typical of the passage of the S wave, which will result into the up and down movement of the ground surface. Then of course we are having other waves, which we say the surface waves, which are done generated at the later stage, and they all mostly they travel along the surface of the crust, and they are termed as the surface wave. The love waves are having very typical motion, okay, which has a mixture of both. Okay, so you are having the particles will move side by side, okay, as compared to what we have seen in the other waves. Okay, so you are having the love waves, and the Rayleigh waves, if you look at, is having an elliptical motion. Okay, so particle will be rolled in an elliptical motion. Okay, so if you remember all four waves, okay, which are the part of the body waves and the surface wave, so none of the motion has been left out. Okay, so either we are having the motion which is having side by side, which moves, or it is moving in elliptical. There is a love surface wave, there is the love wave, and there is a Rayleigh wave. And previously we have seen that they are moving back and forth, and then we are having up and down. Okay, so in short, surface wave will not leave any structure on the surface; it will completely destroy. So the S wave, when they propagated, we at least see some structure is left out, partially damaged, but this will result into total damage. So if you look at the compilation of this seismic waves, what we are having the wave type, then we are having motion, and then the terminologies which have been given or the names which have been assigned to this wave. So we are having, in broader sense, we have body wave, we have surface wave. Motion is longitudinal transverse, that is for the P wave it is longitudinal, S wave it is transverse. Surface waves, for love wave we are having horizontal transverse motion, and for Rayleigh wave we are having elliptical. So in total we are not left out from any side. Okay, all types of motions will be experienced at the time of an earthquake. Okay, and also we try to remember the most important characteristics of the P wave is that it will produce sound, whereas and then again the P wave will not be able to pass through the liquid medium. Okay, so this is again the S wave will not be able to go through that. Okay, so if you look at, just refer to this part, this is an important sections which you should remember. Okay, and then we can move ahead into the different. Okay, so the S wave can only propagate through solid, so this you should remember. And the P wave, what we were talking about, the most important part is that it can propagate through all. Okay, so P waves will propagate through liquid, gas, and medium, gas medium, and then it has a typical characteristics of producing sound here. Okay, whereas the other waves are okay. So this will result into the motion back and forth, and this will move the land surface up and down. Okay, passes only through the, and this we have talked about. So we'll just move ahead. So in short, if you look at the type of motions, we have been not left out with any kind of that. Okay, we see all. Okay, longitudinal transfer, horizontal transfer, and vertical elliptical. So this we experience at the time of the phenomena which we termed as an earthquakes. Okay, so earthquake, in short, what are the earthquakes? What the formation, or this is the process we termed as an earthquake is that sudden release of stored energy, which will result into the vibrations. Okay, and the earthquakes are seen occurring along the weak zones of the Earth's surface. So if you experience the sudden release of an energy, that will result into the ground shaking. Okay, and that process is termed as an earthquake. Okay, so this is an example of the very famous fault system. We will talk about this in our the following lectures, what are different type of faults, but these are the weak zones on the Earth's surface. So whenever there is an earthquake, there is a displacement of the within the crust. Okay, so rocks are moved, and they will have some sort of a displacement experience during an earthquake, and that displacement is will be manifested on the surface. So manifestation of the crustal deformation along the on the crust are termed as fault lines. Okay, so this we will see what are the different type of fault lines and all that. This is a famous fault line of what we say San Andreas fault system in US. It's again the same photograph which shows that over the time when there is an because the earthquake is a repeated process which will keep recurring again and again along the weak zone, and it will keep deforming the land surface. Okay, so the movement which get preserved on the earth's surface along a typical weak zone which we term as a fault line. And here what has happened is that there was an earthquake or the displacement or the deformation which has been manifested on the surface has displaced the landforms over the surface, earth surface, and the landforms are on this displaced or deformed landforms are preserved. For example, here even the streams which are flowing are deflected because there is a movement along the fault which is moving in the boundary over here. Okay, there is the boundary between the two blocks, okay, which have moved. So this block has moved towards us and this block has moved away from us, resulting in the deflection of the streams. So these are all deflected streams we can see here. Okay, so this is the longest one we are having, and then we are having the shortest ones here. Okay, and then this is a fault line which we can see on the earth surface. So this is a best example which has been explained in USGS site, that how we can look at and try to understand that how earthquakes occurs. Okay, so if you can take your both the palms and try to press towards each other and try to slip it. Okay, so of course you are having the friction along this, and then sudden release or you can say the slip along this will produce some jerks on your in your hand. Okay, and those vibrations are your earthquake. Okay, so whenever there is the pressure is there within the earth crust, when we are talking about the two continental or oceanic continental plates are colliding or subducting, then you are having the compression which has been developed on either side, and then over the time the strain will be developed, and sudden release of the strain along these weak zones will result into the vibrations. Okay, and that sudden release of the strain is the process what we call the earthquake. So I'll stop here, but I'll start with this topic in the next lecture, and we'll talk more on the earthquakes and the seismic interior of Earth. Thank you so much.